So we continue on diode part 2. All right. So this one, we have done quite a lot, all this. Okay, today we're going to look through the mathematical, but then other type of circuit, okay, various type of circuit that you can see, and also the graphical method. Okay, so we have done on the Zener diode. Okay, Zener diode is vice versa to the regular diode. So the only difference is this is normal diode, regular diode. So you apply plus at this side and negative at the other side. However, for Zener diode, okay, in order to turn on Zener diode, you apply positive to this curved side of your Zener diode and negative side to the other side. Okay, so this is the difference of symbol in regular diode and Zener diode. Okay, we have done this. So Zener diode is usually used as a regulator, okay, to regulate the voltage output. Okay, for example, you have sinusoidal input, okay, and then you want your output to be fixed at 5 volt, then you use 5 volt of Zener diode as the output. So your output will be clipped at 10 volt because it will be regulated at 10 volt, right? That's just an example. Okay, and then we see the characteristic. Also, this is the characteristic curve. Okay, for the normal diode here, this is forward bias. And then at the negative side here, this is reverse bias diode. And then this is when the Zener diode on. So Zener diode works in reverse bias mode. Okay. So these are the other example. Okay, so I just want to continue here. Okay, so there are two methods, okay, of diode analysis. One is mathematical, okay, where you apply the this one. You're using diode model. Okay, diode model could be silicon diode, where it has voltage drop across the diode. Okay, and then we're going to continue a bit here. Okay, many types of circuit here, and also in the next hour we will do on the graphical. Okay. All right. So for the circuit analysis for diode, okay, so these are the steps, okay, that I have shown you in the previous class. Okay. First, you need to replace your forward bias diode with relevant voltage drop. Means the voltage drop of the diode. If you find out that the diode is in forward bias, means it has voltage drop. For example, if it is a silicon diode, then the voltage drop across that diode is 0.7 volt. Okay, it depends. But usually voltage drop will be given in the question. Sometimes voltage drop will be 0.6 and sometimes could be 0.7 volt. Okay, or and then okay, you skip this number 2 because number 2 is for revert bias case. You skip this, and then if you define that this diode forward bias and you replace with voltage drop is 0.7, for example, and then you perform KVL, okay, across the node. Okay, and then you perform Ohm's law to find any other variable that they need. For example, if they want current, then you apply Ohm's law. For example, your circuit is reverse bias. Okay, what happened when your diode is reverse bias? What happened to your diode? It will be open circuit. When it is open circuit, what will be zero?
Current.
Current.
Current will be zero, correct. Okay, current will be zero. Okay, and then you perform KVL as well as you perform Ohm's law. All right. Okay, next. So these are the example that I've shown you. Okay, so actually I will upload this final slide after class. I mean, with my handwritings here after end of this chapter. Okay, so usually I will upload like that. Okay, so these are the example for forward bias diode. Okay, for forward bias diode, this diode turns on. How you define this diode turns on? At the anode here, it is connected to the positive terminal. At the cathode here, it is connected to the negative terminal. Therefore, this forward bias diode is turned on and it has voltage drop. So you replace with the equivalent circuit in the right side here. So the anode is plus, the cathode is negative. So now you can perform KVL, means you apply loop to this circuit. Okay, when you apply loop in clockwise, it looks like this. So my way is I will choose the first terminal that this current meets. Okay, the first terminal is negative. So the KVL negative V plus VD plus VR. Okay, you know that VR is equal to current time resistor. So the current across this loop is I. So I times R. Okay, I times R equal to 0. Remember that KVL is equal to summation voltage equal to 0. Okay, it's a summation of voltage equal to 0. All right, so this is how you do it. Okay, and then from here maybe they want current, so you find the VR first and then you find current. Okay, so this is the same thing which is I explained in the previous slide. Okay, let's take a look on the reverse bias diode. Okay, reverse bias diode. So this circuit is given. Okay, now I shown you. Now I show you now you already know that this question is for reverse bias, but in a real situation you wouldn't know. You have to define yourself whether this is in forward bias or reverse bias. All right, so this is the connection. So voltage and then diode in this direction. Okay, and then resistor. So you need to define yourself. Okay, now the anode here is connected to the negative. Okay, so when anode connected to the negative, so we know that this diode is in reverse bias, means that this diode is off. When it is turned off, Dr. Izala said it will be open circuit. So you redraw the equivalent circuit, it will looks like this. Okay, open. So the diode will be open and no current flow, current equal to 0. But still, there is a voltage across this open circuit. Okay, if you can imagine it, it is actually equal to the negative of voltage supply. But then if you cannot imagine it, okay, you have to do the KVL. Always go back to the KVL. Okay, so how about the terminal here? So the terminal here will be the same as where this is anode, which is this is plus and this is negative. So plus, negative. Okay, and then you apply here. You know that this current, this is open loop. Okay, open circuit and current equal to 0. Therefore, this resistor will be shorted because current times resistor 0. Therefore, there's nothing here. It will be 0. So if you apply KVL, you will have negative V minus VD plus VR equal to 0 equal to 0. And VD is actually voltage across here equal to negative V. Okay, remember that. Okay, this is how we define the reverse bias diode. All right. So this is a reverse bias diode. Okay, I have explained now. So we have seen this example. Okay, on the forward bias diode. Okay, like for example this example, they didn't mention that this is a reverse this is a forward bias, but you have to define yourself. This is forward bias. Okay, so how is just what I have explained in the previous slide. Okay, so this is forward bias and there is a voltage drop. Then you apply KVL and so on. Okay, we have done this. I hope you understand on this. Okay. All right. Okay, let's take a look on the second example. Oh, sorry. Okay, on the, this is first example. Second. Also, this is a solution. So you can look through the solution. Okay. Now last time we stopped at example 2. Okay, example 2. Okay, I need to and show. Okay. All right. So, oh, I supposed to turn off my video. Okay. Okay. Let's take a look at example 2. So this circuit is given for example 2. Okay. Now you need to define. Okay. So Why trivolt is there? It's okay. All right. So you need first you need to define whether this diode is forward bias or reverse bias. Okay. So let's do together. Okay. So I need to redraw again the circuit. So right. So you have 3 volts. Example 2. Okay, so you have 3 volt here. Okay, you can use either way of drawing the voltage supply, doesn't matter. And then you have negative cathode, and then you have resistor here 2K. Okay, so it is silicon diode 2K, and this is current IR. Okay, so this is the question. So now you need to define whether this diode is forward bias or reverse bias. Okay, so this is the anode. Okay, the plus. Okay, this is the cathode. Okay, let's see. So now the anode here, okay, connected to this negative. So what will be the diode turns to? Is it forward bias or reverse bias?
Reverse bias.
Reverse
Reverse
Okay,
bias.
bias.
okay, reverse bias. Therefore, it will be in reverse
Opposite circuit.
bias. Yes, it will be open circuit. When I write O/C, it is open circuit. Okay, so you redraw again. Okay, you will get something like this, plus minus 3 volt. And then it will be open circuit like this. Okay, plus minus VD. And then you have resistor here. Okay, R, which is R equal to 2K in the question. Okay. Now they ask you what is VD? Okay. What is VR and IR? Oops. Sorry. Okay, IR. All right. So now, okay, to calculate the, okay, at first you know that, okay, so current here equals to what? You know, when open
0.
circuit, current equal to 0. So automatically, you know that IR is equal to 0 ampere. Okay. How about VR, voltage across this resistor? Okay, you know that VR, yes, equal to IR. Okay, so 0 times 2K is equal to 0 volt. Okay, you know that VR equal to 0 volt. Okay, now you need to do KVL across this loop. Okay, but if you can see straight away, you know that VD equal to negative 3 volt. But if you cannot see, then you can apply KVL. Okay, so the KVL would be, so this circle loop. Okay, so my way is I take the first terminal. So you will be like negative 3. Okay, and then you see this first terminal, negative VD, and then you see here plus VR, and no more voltage equal to 0. So this VR you know equal to 0, then VD is equal to negative 3 volt. All right, so that is how you do it for this example. Okay, for this example, that is how you do it. So same like the previous one, but this is with numbers. Okay, I hope you understand this. Okay, and then this is the explanation. Okay, you may take a look if you do revision. Okay, but it is actually the same thing what I have written here. Okay, all right. So
Doctor,
yes.
doctor, is it compulsory to show the KVL equation during the exam?
If it involve no, if you manage to but if for this one it is quite straightforward. Okay, you don't have to show, but if the circuit is complex, then you have to show the KVL. Okay,
Okay, doctor.
all right. Okay. Okay, so we've done the example 2. Okay, so now let's take a look on the next example. Okay, for example 3. Okay, for this one. Okay, okay, I need to put it here. Let's take a look at example 3. Okay, so example 3. So instead of having one diode, okay, now it has two diode. Okay, different type of diode, silicon diode and germanium diode. Okay, and this is voltage supply. Okay, you might be not familiar with this kind of drawing, but don't worry, you can always draw again the drawing. Okay, let's try together here. Okay, so this is example 3. Okay, so given that it has power supply, 12 volt, and then silicon diode, and then germanium diode, and then it has 5.6k volt. Okay, and then uh, you have ground. Okay, let's draw again. Okay, now the voltage here plus. Okay, plus is connected to the plus of silicon diode. Okay, so let's draw again. Okay, you have 12 volt plus, okay, the other one is of course negative, 12 volt connected to the silicon diode. Okay, and then silicon diode connected to the germanium diode. And then you have resistor here. This is ground. Okay, and 5.6k ohm. Okay, all right, so they ask you about the VR here. Okay, VR, and then also IR. So these are the question. So what you need to do, first thing first, is to define, okay, both diode here, forward bias or reverse bias. Okay, can both of you see here? So this is the anode, okay, of the
Forward.
diode plus, yeah. What would be the silicon B? Plus connect to plus terminal. Therefore, silicon diode,
Forward.
Forward.
Forward
forward bias, okay.
bias.
Forward bias, okay. What happened to this germanium where the negative connect to negative terminal? Therefore, this germanium also
Forward
Forward
bias.
bias.
forward bias. Okay. Now we would like to draw the voltage, the equivalent circuit. Okay. So I just want you to know that the voltage drop for silicon for this question is 0.7 volt, and voltage drop for germanium is usually will be given. Okay. 0.3 volt. Okay. Let's draw again the circuit. Okay. So you have 12 volt here. Okay, and then since this silicon diode forward bias, so you will be replaced with voltage drop 0.7. Okay, and then germanium also on, so you will be replaced with voltage drop plus minus 0.3 volt, and then this is your resistor. Okay, 5.6k ohm. All right, so this is how you do it. Okay, now they want you to find the VR. As you can see, when this kind of question give you just like this, okay, just like this, VR. Okay, so where does this VR represent is actually from this particular node, okay, to the ground, to the ground. Okay, so VR is actually this particular node will be the positive and the ground of course negative and equal to VR. So VR is actually represent the voltage across 5.6k ohm. Okay, and then what you would do next is apply KVL. Remember your KVL always clockwise. Okay, in this direction. So this current is IR. Okay, so it is actually the same I lah, same I. Okay, Okay, let's do the KVL. When you apply KVL, you actually following this. Okay, remember. Okay, so my way, I will follow this loop. Okay, can I have different color? Okay, so this is my way. So the first terminal, this arrow C, will be negative 12. Okay, and then first terminal C is plus. Oh, sorry, plus 0.7. Okay, and then next this will see it will meet the positive 0.3, and then it will meet with plus this one VR plus VR equal to 0. Okay, now it's either you want to make it IR times 5.6K, or you can straight away find VR first. Okay, for this case, can you find VR first? Can all of you calculate how much is the VR?
11 volt.
11 volt. Okay, great. 11 volt. Okay, so now you get the VR. Okay, next is to find the IR. Okay, you perform Ohm's law. You know that VR is equals to IR times 5.6K. Okay, so IR here, okay, is equal to 11 over 5.6K. Can someone give me the answer?
1.964 milliampere.
All right, great. Okay, 1.96 milliampere. Okay, so this is how you do this kind of question. It may look like you didn't you didn't know. I mean, you have no experience on first thing, but always redraw the circuit. Okay, it's actually as simple as this. Okay, as simple as this. Okay. All right, so this is the explanation of what I have explained just now, but you can try on your own. Okay, I mean, if you do revision, it's either you want to look at this or the same thing what I have explained here. Okay, okay. Now let's take a look on the other example. Okay, so this is exercise 1. Okay, so for this exercise, I will show it to you. Okay. All right. You have any questions so far? Hello?
No, Doctor.
No. Okay. All
All
right.
good, Doctor.
All right. Great. Okay. So we shall move to the next example. Okay. So for this example, okay, they show you, okay, now negative. Okay, don't get like so nervous with this kind of circuit. So everything go back to basic where you have to redraw again the circuit. Okay, go from terminal to terminal. Okay, point by point. Okay, if you do in ECA class last semester, you always go point by point, to determine your circuit. Okay, your equivalent circuit. Okay, now let's do this together. So this is example exercise 1. All right. Okay. So you have here, okay. Now you have negative here connected to this germanium. Okay. If you are too, you can't wait, then you will see that both diode of reverse bias. You said that, oh, this 10 volt connect to negative, but then no, we have to redraw again. Okay, so we have sorry, where is it? Oh, okay, germanium the other to the left, silicon to the left. Okay, so you have germanium here, and then oh, okay, you have germanium here. Okay, and then you have silicon here. So this is germanium, so this is silicon. So now germanium to negative 10 volt. Okay, to negative 10 volt. So negative here 10 volt, and the other side is of course positive 10 volt. Okay, so what else you have? And then you have resistor 1.2K and resistor 3.3K. Okay, so redraw again. So you have this 1.2K. Okay, and then this you have how much is this now? 3.3K. Okay, so now, okay, now you need to define whether these two diode is forward bias or reverse bias. Okay, so let's take a look here. So this is the anode, this is the cathode, this is anode, this is cathode. Okay, let's take a look here. So this plus now, okay, if I were to take the different color, so this plus now, okay, now connected to the anode. Okay, so what will be the silicon diode be? So it will turns on or off, or forward bias or reverse bias for the silicon?
Forward.
Forward.
Forward bias.
All right, great. How about the germanium?
Same.
Same one, forward bias. Okay, forward bias. All right. Oh, forward bias. Okay. All right. So when I draw now, okay, so this is your equivalent circuit. Okay, you have your equivalent circuit here. So since both that forward bias, it has voltage drop. Am I right? Okay, so you redraw the equivalent circuit, you will get like this. Okay, negative, plus, and this is uh, 10 volt. Okay, 10 volt, and then you have negative here plus, so you know that germanium is 0.3 volt. Okay, and then silicon negative plus, okay, you know that here is 0.7 volt, and then you have resistor here and resistor here. Okay, so this is 1.2k ohm, and this is 3.3k ohm. All right. Okay. Now you have all the voltage drop because all of it forward bias. Okay. So you need to apply KVL right now. Okay. Your KVL. Okay. Previously, okay, let's go back here. Okay, I apply this KVL. So in other examples, so this KVL, okay, always remember that current always going out from the plus voltage, okay, plus voltage. So coincidentally, that this is in clockwise direction. Okay, in clockwise direction where current is going up. Okay, means that it is always going up from this plus terminal. Okay, if you do in ECA, it is also like that. Here also like that. So it happened to be that this is in clockwise where current is in this direction, going up from plus and going back to negative. So this is the nature of your power supply. Okay, so about this one, okay, about this one. So you want to make your loop, okay, you want to do your loop in the right way. So you do it like this. Okay, so current always going out from plus. Okay, therefore I want to, so my loop will be in this direction. So this is my current direction. Okay, so this will be my current direction. Okay, so when current first goes in, so this is plus, this is negative, and this is plus, this is negative. Okay, okay, don't forget that the question said, okay, they want V naught here, okay, V naught 1 and V naught 2 here. Okay, all right. So go back here. So let's do the KVL. Okay, KVL. So let's start from this one first. Okay, this one. Okay, let's draw the KVL. So your KVL will be equals to what? Let's start with the first terminal of minus 10. Okay, minus 10. Okay, minus 10. Okay, and then plus this current times 3.3K. Okay, and then it means the first terminal plus current times 1.2K. Okay, and then the first terminal this current meets is plus 0.7. Oh, too long equation. And the next one plus 0.3 equal to 0. Okay, now can you find the current here? Can someone find the current here? So you have all this equation. Can you find the current? How much is the current? Do you have your calculator with you? 2 ampere. Okay, so your friend said, okay, Zenzian said 2 milliampere. Is that right?
1.64 meters.
Yes, doctor.
Same.
2 milliampere. Okay, who said
Yes,
just now
yes.
1 point something something? But 2, right? 2 milliampere. Okay, 2 milliampere. All right. All right. Okay, so you have your current 2 milliampere. Now your objective is to find this V01 here. Okay, and V02 here. Okay, now let's take a look. Okay, your V01, like I said just now, from that particular node. Okay, let's go back here. Okay, so this VR is actually represent, if this VR node is here, means from this node to the ground. Okay, so let's take a look here. So for this case, VR from this node to the ground. Okay, for this case, okay, and for this particular case, so VR here is current going from this node to the ground, means plus minus. See, plus minus. So it will be multiplied with plus IR equal to plus VR times 5.6K. Okay. However, for this one, okay, as you can see, now current is going to the opposite direction. Okay, so can you find the current? Let's say for the current V02. Okay, V02 now, this point is connected to the negative. So V02 now is equals to, means that negative V02 equals to current times 3. Oh, hello? Are you still there? Hello, student?
Yes, yes, doctor.
Oh,
Yes.
so suddenly my PC going to sleep. But may I know what are you seeing now in the screen?
Yes, doctor.
The same example, the same exercise, right?
Yeah. Same.
Okay, okay, okay. Oh my God. Okay. All right. So times 3.3K. Okay, we know that because this node V02 is connected to negative, therefore negative V02 equal to I times 3.3K. So V02 is equals to negative 2 milli times 3.3K, which is equal to negative 6.6 volt. Okay, 6.6 volt. All right. Okay, now let's take a look on the V01. Okay, V01. Okay, so like I said, so V01 is now here. Okay, here. Okay, so I said that from that particular node to the ground, right? To the ground. Okay, let's take a look on this V02. Okay, V02 from this node to the ground. Okay, what do you see from this node to the ground? Only resistor 3.3K. Therefore, V02 is equal to negative current times this 3.3K. Okay, let's take a look at V01. So V01, okay, so along the way from this V01 to the ground, it not only has 1.2K, so it has negative 1.2K times negative 3.3K to the ground. So see that V02 from this particular point to the ground, it has to meet two resistors, 1.2K and 3.3K. Therefore, to define your V01, okay, V01 is actually equals to negative 2 milli times resistor 1.2K, okay, and minus negative 6.6 volt. Okay. Why 6.6 volt? Because V02 you already calculate minus 6.6 volt. Okay, it's equals to, oh my god. Okay, it is equals to negative 9 volt. Okay. Oh, okay, negative 9 volt. Oh, oh my God. I don't know why. Okay, so it is equal to negative 9 volt. So V01 negative 9 volt and V02 negative 6.6 volt. Okay, so this is quite challenging where, because why is it challenging? So I think to define whether it is forward bias or reverse bias not so challenging. So the challenging part is where you define the V02 and V01. Remember that current, your loop, okay, your loop, current loop always defines your positive and negative terminal. Okay, why I make this current in counterclockwise? Because you know from the ECA, current is always going out from positive supply and go back to negative. Negative is always ground lah. Basically, you can't see here, but in real circuit, it is actually go back to the ground. Okay, so that's how you define this loop. And then when the current in this direction, so this will be the plus. Okay, the top one will be negative. But then the question asks you to find V02. And V02 automatically, you know that it is connected to negative. Therefore, if you measure by using simulator, multi-sim, okay, you will get negative V02 because that this V02 connected to the negative terminal. Then you will get that 6.6 volt. Right? So this got the answer here, but the solution like I have shown you in this slide. Okay, all right. Do you have any question before I move to the other exercise? I think I think I should show you many type of circuits so that you will be familiarized with any type of circuit given to you. Okay, especially with this kind of circuit. Okay, where you connect negative first to the diode and then go back to your ground. Okay, it is actually look like complicated, but then if you redraw from point to point, you will get the answer. Okay, you will get the equivalent circuit like this. Okay, do you have any question before I move to next exercise?
No questions, Doctor.
No question. Okay, all right. Okay, so we shall move the next exercise. Okay, this one. Okay, this is quite pretty straightforward to me. Okay, all right. So in this example, okay, okay, answer given, but then let's take a look here. Okay, so look at this example. Okay, from your sharp eyes, okay, okay, what can you see here? Okay, so you have voltage supply here. This is plus, minus, okay, and then you have diode. Now, instead of in series, it has in parallel. Okay, the previous example that I have just seen is this diode in series direction. Okay, series, where in series, you know, in series, right? Okay, series. So these are in series. Okay, this also in series. This is in series. Okay, now these two diode in parallel. Although it is in parallel, you need to define whether it is forward or reverse bias. Okay, so let's don't get nervous if you get this kind of question. Still go back to the basic. Okay, so you have your anode here, plus minus plus minus. So now this plus is connecting here. Okay, so what happened to these both silicon diode? Are both forward bias or reverse bias?
Both forward bias.
Correct. Forward bias. Okay. Both are forward bias. Okay. Forward bias. Okay. So this question asks you to find, okay, so what will be the, okay, my simple question. If it is forward bias, okay, now you can redraw the equivalent circuit, right? You can redraw the equivalent circuit. So let's redraw the equivalent circuit here. Can I conteng somewhere around here? Oh no, I think for proper one, it will be messy if I draw it here. So I will draw it and in different slide. Okay, so that you can always refer in a proper mode. Okay, so this is exercise 2. Okay, now you already said it is forward bias. Therefore, when it is forward bias, it has voltage drop. Let's draw again. So you have plus minus 10 volt here. Okay, and then you have what do you have? 0.33 k ohm. Okay, and then you have diode here. You know this diode forward bias plus minus. Okay, plus minus 0.7 volt, and then you have plus minus 0.7 volt. Okay. Okay. So the question asks you to find, what is that? ID1, ID2, and I1. Great. Okay. So they want you to find I1 and then ID1 and then ID2. Okay. So my simple question here. So can someone give me what is V naught? What is V out here? What is the value for V out? Let's do some revision on the ECE.
0.7 volt.
Correct. Okay. So it is 0.7 volt. Thank you. Why it is 0.7 volt?
Parallel reaction.
Yes, it is in parallel. Okay. So this V naught, okay, this V naught is in parallel with this diode. Okay. Therefore, it is 0 voltage drop across it is 0.7 volt. Always, because it is in parallel. Okay, always the voltage drop here is 0.7 volt. All right, now let's take a look on the how to find the current. Okay. Okay, now I want to find current. Okay, now let's go. Okay, now let's decide how to define the current. Okay, now you need to find current I1. Okay, current ID1 and current ID2. Okay, do you still remember KCL? KCL, my dear student?
Yes, yes.
Yes, yes. Okay, so KCL, so we apply KCL, okay, at this node. Okay, so you know that KCL is current. Okay, in ECA you have learned this. Current in equal to current out. Okay, total current in equals to total current out. Okay, so at this particular node, current in is what?
I1.
Correct. I1. Okay, it is I1. Okay, I1. Okay. So is there any current in going into this node? Any more current in?
No, only
No more.
I1.
Yes, correct. So what will be the current out from this node? Going out from this node. So
I01
you,
and I02.
yes, you have ID1. Okay, and also going out here is
So,
ID2. Okay, so this is the method to find all these variable needed. I1, ID1, and ID2. Okay, so the only way to solve first is by using KVL. Where? At this node. Okay, you apply KVL. Okay, at loop. Okay, so when you apply KVL at this loop, okay, so let's take a look of this example. So the first one, so this loop, okay, first one, this arrow meets is -10. Okay, and then plus current I1 times 0.033K. Okay, and then it meets what here? Plus 0.7 equal to 0. Okay, remember that it always, since it is parallel, so the voltage drop across this node only 0.7. Therefore, only one voltage involved here, 0.7. Okay, it is in parallel. Okay, so now can you find current I1 from here? Hello?
Can.
How much?
Wait.
Okay, I cannot see all of you, whether you're doing it or not, but I hope you're doing it.
ah,
Okay.
the
Best
end,
Jan,
the end.
best said Zen, Zenjan said 28 millimeter pula. 28 milliampere. Okay, 28 milliampere. So all of you get the uh same
Value.
yeah, same value. Great. Okay. So now you want to define, so you get the I1. Okay. Now you want to define your your current at this one, ID1 and ID2. So someone might say, there is no resistor here, doctor. So how could you define the current? So you know that inside, we have learned in the previous lecture. So inside diode, it has internal resistivity. Okay, if you still remember, it has the internal resistivity. Okay, if you were to find this where you can't see the internal resistivity, therefore, since these two diodes are the same type of diode, so we might see that ED1, sorry, ID1 is actually equals to
82.
ID2. Yes, equals to ID2. Now, can you get, I need to mute someone to mute. Okay. All right. So ID2, okay, ID1 equals to ID2. Now, can you get ID1 and ID2 since that I1? Okay. Not proper here. Okay. So meaning that I1 is equal to 2 ID1, let's say. Okay, so can you get ID1? Yes, ID1 is equals to 28 milli over 2, which is equals to 14 milliampere. Okay, that's how you get ID1 equals to ID2 also 14 milliampere. All right. Okay, so I think with this example, you have at least you have idea on what happened to diode in parallel connection, parallel configuration. So this is in parallel. So this is how you do it. Okay, this is how you do it. Okay, so this is the answer. So this is the solution. Okay, so I think, okay, do you have any question regarding this example? If no, I can move forward to the next example. Hello?
Doctor,
Yes.
Yes,
Can.
yes, yes,
Yes.
if
yes.
we have the current of the diode and the voltage through the diode, can
Uh-huh.
we find the internal resistor using
Oh,
the Ohm's law?
yes, can. If they will ask you the question, the internal resistor, then you can find the internal resistor equals to 0.7 volt divided by 14 milliampere.
Okay, doctor. Thank you.
All right. Okay. All right. So let's move to the next exercise. Okay. So I hope all of you um, understand. Okay, on the previous slide. Okay. Now this example pula. Okay. Okay. So this example. Okay. Okay. Find the ID when the diode is ideal. Okay. So this one I haven't mentioned. I think I haven't mentioned anything before. Okay. So previously we have seen this. Okay. So this is not ideal diode. So this is silicon diode. Okay. As well, this is germanium diode. Means when it is turned on, it will have a voltage drop. Okay. For example, this one, both are turned on, therefore the voltage drop is 0.7. Okay. However, this is ideal diode. So this question said this is ideal diode. So ideal diode, it can be turned on and turned off, but it doesn't have voltage drop across it. Okay, so let me give you, for example, if you have diode here, okay, so for example, you have voltage, you have diode here, and then this you apply plus and then negative to here, plus negative. So you know that this diode is forward bias, right? Okay, if let's say it is silicon diode, means it has voltage drop 0.7. Am I right? Okay, am I right? Okay, but if let's say this is ideal diode, it can allow currents to flow through. It is not open circuit, but then it becomes short circuit like this. But there is no voltage drop. It's just a short circuit like that. So it allows current to flow through, but no voltage drop. Okay, so how it works? Okay, let's take a look at this example. Okay, so this example, it has 30 volt. Okay. Okay, so this example, exercise 3. Okay, so you have 30 volt here, plus minus 30 volt. Okay, and then you have resistor here is 1 k ohm. Okay, and then you have resistor here, much just now, 1 k. Oh, all 1 k, 1 k, 1 k, and they want ID. They want the question ID. Okay. Okay, this is 1 k ohm, and this is how much this now? 1 k ohm also, and this is ideal diode. Okay, so let's draw the equivalent circuit. Okay, so first, not draw the equivalent circuit. Let's define whether this diode is forward bias or reverse bias. Okay, so you know that this ideal diode, of course, it has terminal. This anode is plus, this cathode is negative, and this positive terminal is in this direction. Okay, in this direction. So this positive terminal in this direction, and it meets the anode. So what happened to the ideal diode, my dear students? Is it forward bias or reverse bias?
Forward bias.
Yes, forward bias. Okay, forward bias. So now, let's draw the equivalent circuit. Okay, like I said just now, okay, the equivalent circuit. So let's take a look here. Okay, so you have here 30 volt, okay, plus, minus, and then you have here 1K, okay, and then you have here 1K, okay, and then you also have here 1K, okay. Like I said just now, it is forward bias, therefore it allows current to flow through. Okay, it allows current to flow through. So meaning that it is become short. Okay, short. Okay, no voltage drop, but it become shorted. Are you clear with the ideal diode behavior, student?
Yes, doctor.
Okay, remember, okay, for ideal diode, it allows current to flow through and it becomes shorted. However, for practical diode like silicon diode or germanium diode, it allows current to flow through, but it has voltage drop. Okay, remember that. Okay, so now this is ID. All right. So okay, so now you want to find your ID. Okay, your ID. Okay, so how do you find your ID? All right. So can I redraw? You can do like the other method just now where you apply KCL at the nodes, or you can also do the equivalent circuit. It is up to you actually. Okay, it is up to you. Okay. So now, okay. Um, Okay, so how you do it? Okay, for example, I want to do like KCL stuff, something like that. Okay, so can I actually redraw the circuit become like this? Okay, so that you will be like familiar, okay, the circuit. Okay, you can always draw the circuit according to what you're familiar with. Okay, so this is 1K. So can I draw instead of this resistor vertically, can I draw like this? Is it will be still
Can.
the same? Can, right?
Yes.
Okay, yes, can. Why I draw like this? So it will be much clearer for all of you. Okay, so this is ID. All right, so this is ID. All right, so can you find this ID? How do you find this ID? You have,
30
is it
over
what?
2 kilo ohm.
Again?
30 watt over 2 kilo ohm.
Uh, th
50 milliampere.
30 volt over 2 kilo ohm. Why 2 kilo ohm?
Short circuit.
Mm-hmm. Other student?
Madam, I think
Mm-hmm.
I can simplify the circuit first. From
Yes.
the parallel circuit 1K and 1K, it
Uh-huh.
becomes 0.5K.
Uh-huh.
So I can calculate the current through resistor 1K.
Uh-huh.
So 30 volt divide by 1.5K. So I can get the current.
Okay, that one also can. Okay, so correct. So you can actually parallel this resistor. Now you have two loop. Okay, you don't have to do like what do you learn from the ECA? Meshing? Okay, that is you can apply meshes here. Okay, but there will be a very long procedure to do it, the mesh. But if you like mesh, then you can do mesh. Okay, after all, you can also do like this. Okay, you can parallel these two resistor. Okay, so our total will be equals to 1K parallel with 1K. So how much do you get here? Hello?
0.5.
Okay, 500 ohm. Okay. Okay, so this loop, okay, will become the equivalent loop like this. Okay, you have plus minus. 30 volt, and then you have 1K here, and then you have resistor here, 500. Okay, 500. Okay, 500. So you apply KVL here. So for example, I want to make a notation here. Okay, so this is my I1. So this is my I2. So this is ID. Okay, doesn't matter there. Okay, ID. So now for this case, okay, can you find this I1? Can, right? So you will get I1, okay, if you apply KVL, negative 30, and then plus I1 times 1K, plus I1 times 500 equal to 0. So you can get your I1 is equals to how many?
1 milliampere. 20 milliampere.
20 milliampere?
Yes.
Okay, 20 milliampere. Okay. Now, my question is, this I1 is at this point I1. Can you find I2 and ID? So what will be the I2 and ID? Can I say I2 and ID are equal?
Yeah, you can.
Yes.
Yes. Why? Because it is in
Parallel.
parallel. Okay, voltage across here is parallel, and you can see that resistor also same, therefore the current is also same. Okay, therefore if you apply KCL here, you know that I1 is actually equals to I2 plus ID. Okay, now that I1, okay, so I1 is equals to I2 plus ID. And we know that I2 is equals to ID. Okay, therefore, ID is equals to I1 over 2, which is equals to 10 milliampere. All right, so that's how you do it, okay, for this exercise. Okay, so it is actually the same thing what you have learned in the ECA, but then you have diode in it. In ECA, you don't have diode in your circuit, but here you have diode. Okay, so every time, okay, when you can also apply mesh if you want to make sure you are in the, because mesh is, student love mesh, right? Student love mesh instead of nodal. Okay, so you can apply straight away mesh. Okay, but this is the simplification circuit, because I do this because both the resistor are the same, so I expect that the current also the same. Okay, so this is the final answer. This is the solution. Okay, if you do the revision, you can take a look this solution. All right, so okay, so can we have we can have 5-minute break. Okay, if you have any question, you can ask me. Okay, I think I can show again the attendance. Wait. Okay, let me show again the attendance just now. Okay, if you have question, you can ask. Okay, can you see the attendance? For those who didn't not manage to scan your attendance just now, you may scan it now. Okay, students, if you have question, you can ask me. Okay, clear or not with the example and exercise just now, and also if you have any question other than this, you may ask as well. Okay, are you clear so far on the series and parallel diode? Very much clear?
Yes.
Very
Yes,
much
Doctor.
clear, right? Okay, great. Okay. So all of you done with this attendance? I hope all of you can catch up, okay, with this. I think I have been quite slow because I put many example and exercise, but then that's okay. Okay, that's okay, because if you understand now, okay, you will understand. If you see a lot of example now, and then you will understand in the next class, okay, because we're going to carry this concept of forward bias and reverse bias diode in the next chapter, okay, next chapter. That's okay. All right. Let me take a look how many students here in this 49. Okay, right. Okay. Are we done 5 minutes or not yet? Can ask me if you have any question not clear somewhere, to let me know, okay? Can you please share the attendance again? Oh, sure. Here the attendance. Okay, make sure you scan the right attendance. Okay, because I have too many students and too many code in my section, so you can choose yours. Okay, the difference is SEEE, the new code, and SKEE, the old code. Okay, done. All right. So, okay. I think we shall continue. Okay. I think I'm not going to finish all of this. We can continue in the next class, but it's okay. I want to finish these exercises. Oh, we have done a lot, right? That's okay. Please do your own revision on your own. Okay, so that it will be much clearer. Okay, I like this question. Okay, I like this question. All right, find I. Okay, first you need to determine whether this diode is on or off. Can, am I right? Okay, now you have two types of diode in opposite direction. Okay, in opposite direction. Okay, all right, so let's define. Can I just conteng on top of this? Can. Okay. Can you just can you define it? The first this diode, okay, the first silicon diode, the top silicon diode is forward bias or reverse bias?
Forward.
It is forward bias. Okay. Oh, so forward bias. So because this is plus the anode, cathode, anode. So this first diode is forward bias because the anode is connected to the plus terminal. Okay. How about this diode?
Reverse.
Reverse bias diode because the anode connected to negative. So this would be in reverse bias. Okay, I just want to draw the equivalent circuit next to here. Okay, so let's draw together. I mean myself, you just take a look of it. Okay, plus minus, okay, 10 volt here. And then you have this diode, the first silicon diode forward bias. Therefore, it has voltage drop, right? So plus first, and then negative, yeah, 0.7 volt. Okay. And then you have reverse bias here. So what happened to this silicon 2 diode, reverse bias? What happened?
Open circuit.
Open circuit.
Correct. So it will be open circuit like this. Okay, open circuit like this. And then not to forget, you have your 10 ohm here. So draw it again, back 10 ohm. Okay, 10 ohm. All right, now, okay, so this circuit is open like this. So what happened to this 0.7 volt? It is hanging open like that. So you can actually ignore this. Okay, so the equivalent circuit is actually can be turned into like this. Okay, so you have 10 volt here, and then you have 10 ohm here. Okay, now you want to find current I across here, current I across here. So can you find I? So what will be the I?
1 ampere.
Tak ada jawapan kat situ. Kalau tak tahu, tak sangat tak fokus. Okay, 10 over 10. Okay, 10 over 10 is 1 ampere.
Ampere.
Okay, correct. Okay, great. Okay, so this is quite straightforward, but I think this is interesting. Okay, so the diode is on in opposite connection. Okay, so let's take a look at exercise 5. Okay, so I leave this exercise 5 on your own so that you can do it yourself and make sure you get the correct answer. Okay, so you don't have to apply a mesh or so on. You can apply just equivalent circuit and also KVL. Okay, KVL and KCL. That's all. Okay. In the next class, I want to see whether you get the correct answer or not. Okay, can you try on your own later?
Yes.
Okay, correct.
Yes.
Okay. So let's just define whether this diode forward bias or reverse bias. So what happened to diode D1? So this is anode, cathode. So this diode D1 is
Forward.
Forward bias.
okay. Okay. So since this is silicon diode, it has 0.7 volt. Okay, silicon diode. So diode 2, what happened to diode 2? Plus, minus. Therefore, diode 2 is also
Forward.
forward bias, and it has voltage drop 0.7 volt. Okay, that's how you do it. Okay, so I just want to give you some hints so you can apply KCL here. Okay, KCL here. Okay. So I hope you can do it yourself. Okay, and get the answer. Okay, let's see in the next class whether you get the answer or not. Okay. All right, so next one is graphical. Just want to touch a bit on the graphical one and then one example, and then we may continue in the next class lah. Okay, all right. For graphical, using actual characteristic and also load line analysis. Okay, if you can imagine, load line analysis means you have your characteristic of diode. Okay, you have your characteristic of diode. For example, okay, what is your characteristic of diode? Okay, characteristic of diode means the IV characteristic. For example, you have regular diode. Okay, you have current versus voltage. Okay, you know that this is your characteristic. Okay, your IV characteristic. Okay, so this is what is the point of this node? It is what voltage here?
Knee voltage.
Knee voltage, correct. Knee voltage or voltage drop. Okay, knee voltage or voltage drop. Okay, when it reaches the voltage, knee voltage, so current start increasing. Okay, so this is your characteristic of IV characteristic. Okay, now you want to find, okay, in the previous slide, you do mathematical method, okay, to find the current in the circuit, okay, and to find the voltage of the circuit. So you do mathematical where you apply KBL and KCL. Now you want to do some sort of a graphical where you apply load line to your circuit, okay, load line. Okay, so load line means you need to find one node here and one node here, and then you draw the line here, okay, in order to get one node at x-axis and one node at y-axis. There is a ways to do it, okay, but when you connect these two nodes, you will get an intersection point. Okay, your load line. So this is what we call is your load line. Okay, so there is a way to find the load line, but this is your IV curve. Okay, so the intersection of your IV curve and the load line here, this node, is we call it as a Q point. Okay, Q point. Okay, where it is the active point. Okay, from this Q point, you actually can find your voltage at Q point, which is VDQ and IDQ. So this is your objective. Okay, this is your objective. So usually in this part of in this method, okay, so the IV curve will be given, and then your circuit will be given. You are now has to find your load line, this line. So how do you define? How you define this load line is by doing approximation. Okay, so you need to find point at y-axis and point at x-axis, and then you draw a line, this load line. So this intersection, okay, will give you the Q point of VD and Q point of ID. Okay. All right. So what is DC load line? So it is a simple diode circuit where ID and VD are not known. Okay, so not known. We don't know the value of ID and VD of that simple circuit. Okay, we don't want to do the mathematical. We want to do the graphical. Okay, so simple analysis use diode characteristics. So diode characteristic means the IV curve just now, and then to obtain the Q point, the operating point. Okay, the operating point. So nonlinear diode has known the IV characteristic. Okay, the IV characteristic, which is what I meant here. So this curve, this is the IV characteristic, will be given. Okay, now you need to find the load line in order to draw the Q point. Okay. All right. So when nonlinear device is placed in series with a linear circuit consisting of resistor and voltage source, so this relationship between the current voltage in linear part of the circuit represented as a load line. Okay. So this is your load line. Okay, this is what I have shown you just now. This is your IV characteristic, and you have to define this load line. In order to define this load line, you need to draw to get these 2 points, point here, point number 1 and point number 2. Okay, so this intersection will give you the operating point, or we call it as a Q point. Okay, from this Q point, you will get that VD, okay, at Q point and ID at Q point. Right. Okay, So a load line is actually represents the response of a linear circuit, okay, connected to the non-linear device, okay, in question, and also to find the exact value of the current voltage. Okay, so exact value of the current and diode voltage means that this is this ID at operating point and VD at operating point. Now we not known, we didn't know yet the value. You have to find by using graphical. So what are the steps to define the graphical? Okay, like I said just now, you are given a circuit. So this circuit are given. Okay, so this circuit are given. Okay, so now we didn't know yet. Okay, so this is actually we didn't know whether we don't know whether this is silicon diode. We don't know what type of diode is this. Okay, we don't know what type. Handwriting. Okay, we don't know what type of diode is this. Now you want to decide this type of diode means you want to find this VD, okay, by using graphical method. Okay, so you're given this circuit. Okay, you are given this circuit. Okay, like I said, your first objective is to find the first point here, the first point, and the second point here. Okay, in order to draw the intersection line. Okay, to draw the line, the load line. Okay, first you are given, for example, this is just an example. Okay, you are given this kind of circuit. So your first step is to get the KVL. Okay, it's to find the KVL. Okay, what will be the KVL of this circuit? So for example, this represent as ID. Okay, so voltage across here represent as VD. Okay. Now the KVL will be, so KVL will be equals to -4, okay, or if we want to draw, okay, negative VS, okay, plus ID times 200, okay, plus VD equals to 0. Okay, so this equation will turns into like this. So you're gonna have like VS is equals to 200 ID plus VD. Okay, now like I said, you want to find the first point here. Okay, so if you want, okay, for example, students, if you want to find this first point, okay, what will be, so this is y-axis, this is x-axis, if you forget, okay, so any linear equation you have, so for example, if you want to find the first point, what will be equal to 0? What equals to 0?
S.
X equal to 0, correct. Okay, so for this case, x equal to 0. Okay, x equal to 0. For second point, if you want to find the second point, which is at x-axis, what will be equal to 0? Y equal to 0. So from this equation, okay, from this equation, so we know that VD is at x-axis, ID is at y-axis. Okay, so if you want to find the first point, okay, now first point is at y-axis, okay, at y-axis, therefore x equal to 0. Okay, for this equation, x equal to 0, x is VD, therefore x equal to 0. Now ID will be equals to Vs over RL, which is 20 milliampere. So this is your first point. Okay, first point. All right. So the second one, okay, the other note, y equal to 0 means that, so if you have Vs equals to ID RL times Vd, now who equal to 0 when y equal to 0 means that this portion ID equal to 0. Okay, therefore Vd equals to 4 volt, and this is second point. Okay, so I repeat, so the first point is at y-axis. Okay, the second point is at x-axis. Right. So do you clear? Do you have any question before we move forward? No. Hello? Student? Hello?
No.
Student? Okay, no question. Great. Okay. All right. So this is the next one. So this is the solution. Okay. Now you have 2 points. Okay. One 20 milli and the other one 4 volt. Okay. 4 volt at x-axis, 20 milli at y-axis. Okay. So don't get confused with this. So in this question, this curve, okay, this IV curve, okay. So this IV curve is given. Your job is to draw this DC load line. Okay, how to draw the DC load line? Okay, go back to your answer. So your first point just now is 20 milliampere. So this is already in milli. So this is your first point. Okay, first point here, 20 milli. And the second point just now is 4 volt. Okay, this one, 4 volt. This node. Okay, this is your second point. All right. So from here, you need to draw the line. Okay. So this draw, I'm not going to draw on this line because it's already nice here. So draw, connect these 2 points and you will get your DC load line here. So this draw line is your DC load line. Okay, so the intersection of this IV curve and also your load line, you will be able to get your Q point here. Okay, your Q point. Therefore, from this Q point is actually you can extract your VDQ and IDQ. Okay, so basically in the exam or in the test, they will give you this IV curve. Okay, IV curve, you have to draw the IV curve on top. You have to draw the load line on top the IV curve given. Okay, so I'll show you the example later. Okay, so that is how you find. So meaning that for this particular circuit, okay, for this particular circuit, we know that the voltage drop or the voltage diode at operating point, now we know it is actually 0.8 volt. So we can assume it is maybe a silicon diode. Okay, so you might get like 0.78 something or 0.6 something. So it is approximately to the silicon practical diode. So you may assume that this diode is silicon diode. Okay, now for graphical method, you define yourself what type of diode is this diode, how you do it by using DC load line, by using this. Okay, now you know that the operating point of VD is 0.8 and current flow to it is 16 milliampere. Okay, 16 milliampere. All right. Do you have any question before I go to the next slide?
No,
Okay.
doctor.
If you, let's say, if you want to do checking lah, for checking, okay, student. So for checking, I want to use checking, what color? Green color. Okay, checking. So let's say you apply KVL. Okay, you know you apply KVL. This is just now they said that 0.8, right, student? So if you apply KVL, so this is -4 plus I 200, okay, and then you plus this voltage VD is 0.8 volts equal to 0. Now let's just to check, okay, whether it is the same or not. So current here, can you calculate here? So how much is that? 4 minus 0.8 divide 200. How much you get?
16 milliampere.
Yes, 60 milliamperes. So this is quite an ideal example lah. So you get like 16 milliampere. So approximately equal to what you have gotten here, 16 milliampere as well. Okay, but you cannot choose. Okay, doctor, can I choose the mathematical instead of graphical? No, the question decide for you whether you have to use graphical or mathematical. Okay, usually both question lah ada. Okay, both question got. Okay. Can I move forward, my dear student? Do you very much clear on this?
Understood, Doctor.
All right. Okay. Okay. So this called saturation and this called cut off. Okay, saturation means at maximum point of current. Okay, so the current saturate at 20 milliampere, so cannot go further than this. And this is during cut off where the no current flow, but there is a maximum voltage, means that cut off. Okay, current is 0. Okay. So the operating point is 0.8 volt, 16 milliampere, and you can calculate the static resistance, okay, which is equal to V over I, which is equal to 50 ohm. Okay. So now, these are your circuit. Okay, this is your circuit. This is your circuit. Okay, you have voltage, you have resistor. Okay, to control the current flow through into the circuit, and then you have diode. But this, the value of this resistor, as well as the value of this voltage source, will do affect. Okay, could you please give the slide in e-learning? Sorry, I just read it. Will you please give the slide later on? Yes, I already upload the slide on e-learning. Tasnim? All right, so, oh, you mean the latest slide? I mean the slide with my bad handwriting here? You mean that one?
Yes, Doctor. Easy to understand.
Okay, I will upload by excuse for my handwriting, okay?
No, it's okay, Doctor.
All right, okay, okay. So I will
Thank you,
upload
Doctor.
after class. All right, okay. Oh my God, my handwriting. That's okay as long as you understand, okay? Okay. Yeah. Where were I just now? Okay, so this value of the load resistor as well as the voltage affect the Q point. Okay, affect the Q point. Of course, it will affect the Q point because if this value changes, okay, if this value changes, this resistor and this voltage, so this point, first point and second point also changes. When first point and second point changes, so this Q point also changes as well. Okay, it's either going downward or upward. Okay. So this effect, okay, so the effect of RL and VS on the DC load line, of course, okay. So how about when RL is fixed and VS is changes, okay, now RL is fixed, okay, fixed value. Now VS changes. So meaning that, so if this VS increase, so ID also increase. Okay, if the VS decrease, ID also decrease. So if you can imagine, the Q point will move will shift downward and upward. The slope will not change, but the Q point is changed. Okay, it's either moving downward like this or upward like this. Depends on the value. All right, for the case 2, okay, what happened if VS fixed? So this VS fixed, now RL changes. So if this RL increase, so this ID will decrease, maybe at this point. If this RL decrease, so this ID increase, so will be at this point. So this is how we change the Q point. Okay, the slope is changes, okay, as well as the Q point will go upward and downward. So the operating point will be going upward or downward, depends on the value. Okay, okay, all right. Okay. So reverse, okay, so the load line could be reversed, okay, but this is very, might say rare case, okay. So the Q point is always at 0. So when it is reversed, therefore you will get like, so this is reverse bias diode like this. So for the normal diode, it behave like this, right? Okay, for reverse bias, it's 0, right? Okay, so no point. If we draw the load line, okay, it will fix the Q point at y-axis, which is always equal to the negative value, BD. Okay, so as the negative value ID. Okay, so this is for the reverse bias diode. Okay. Okay, if we can summarize this, okay, the load line plots all possible current ID condition and all voltage applied to the diode in a given circuit. Okay, so it depends on the, so this Q point, okay, will shift upward or downward, depends on the value of the resistor and the voltage. So maybe the question will ask you after you draw the load line, so they will ask you what happened if the resistor RL increase. So you might have to explain on the shift of the load line. It's either shift upward or downward. You have to imagine, or you have to go back to your equation. Okay. All right. So why does the resistor is necessary when a diode forward bias? I think I have mentioned it many times. Why we put resistor in the diode circuit? Student, are you still there?
Control the current flow.
Yes, to control the current or to limit the current. Okay, so that there will be no, if you connect power supply directly to the diode, okay, without a resistor to limit the current, you might apply excessive voltage to the diode. Your diode might be damaged, okay, especially when you have silicon diode, very sensitive, it will be easily damaged, okay, by that, okay. That's why a series resistor is needed to limit the current and to avoid your diode become damaged. Okay. Next question, what would cause the barrier potential of a silicon diode to decrease from 0.7 volt to 0.6 volt? Okay, barrier potential means that this one, when you have this one, you have PN junction, okay, you have P, you have N, and then this is your PN junction. Okay, what cause, okay, when you apply forward bias or reverse bias, you will have a depletion region. You used to remember, students? So this depletion region, okay, will have barrier potential. Okay. So what caused this barrier potential to decrease from 0.7 to 0.6, for example, in this case? What caused it? What have you learned? What caused?
Temperature.
Yes, correct. Temperature. I think I only mentioned temperature. Okay, for the diode. Okay, I mean, what what factor affect the potential barrier or the movement of electron to pass through faster or slower is because of the temperature. Okay, temperature. I think I only mentioned 1 point, temperature. So a temperature increase will cause the barrier potential to decrease. Okay, the higher the temperature you put, okay, the more electrons pass through this barrier, okay, then this depletion region will become decreased and potential barrier also decrease. Okay. All right, so for the diode analysis, so this one I will continue in the next class. Okay. Are you all okay with so far the lecture? Are you all
Yes,
still
okay.
there? Still there?
Yes.
Still
Still
hanging there
okay.
with me?
Yes, doctor.
Good.
I hope you all still there with me. I didn't go too fast, not too slow as well, but we I hope if you're not on track, that's okay, but we can always have class, extra class, but I hope you understand. Okay, so far. So we will continue on the diode analysis in the next class. Okay? All right. So if you have no more question, I think wait, sorry. Yeah. Okay. So I just want to show you. So this is past test question. Okay, past test question. Test question. So given this kind of circuit, okay, you are asked to determine using load line. So this is why I said the IV characteristic given. So when IV characteristic given, so this IV characteristic given, so you have to draw your load line on this IV curve. Okay, so it is quite accurate lah if you do it on this per IV curve sheet given. Okay, so this is how it looks like for the past test 1 question for load line analysis. Okay, I think easy, right? You can do it if you understand. Right. Okay. We shall look at this example in the next class. Okay. Student, still there?
Yes.
Yes.
Yes,
All
doctor.
right.
Yes, doctor.
Okay. Great. I hope you. Okay. So your friend asked me, your handwriting really good. No. Temperature, correct. So doctor, does the amount of doping affect? Correct. Correct. Jinhua, the amount of doping do affect also not only the temperature but the amount of doping concentration do affect the depletion region. The more doping of the N type, the more we expect free electrons to pass through. Okay, the more free fast electron pass through, and it's actually creating a less depletion region. Okay, it do affect other than temperature. All right. All right. If you have no more question, welcome, Jianhua. Jianhua. Okay. So you have no more question. So Liu Peng'ang, doctor, is value of voltage supply affect value of voltage supply affect value of voltage supply affect. Yes, it do affect. Okay. So value of voltage supply affect because the more you apply voltage and it reach greater than the knee voltage, so more electron can pass through and it will increase more current. Correct? It affect as well. Peng Ang, am I answering your question? Okay, thank you. Welcome. All right, if no more, we shall end our class now. I will upload as soon as possible the slide as well as the video. Okay, the video, pre-recorded video. Okay. Chong Zinsu asked, doctor, if two different type of diode like silicon and germanium in parallel, it cannot be happen. Okay. Cannot be you put two parallel diode with two different voltage drop in parallel, because parallel should have same voltage drop. You cannot put the two different type of voltage diode in parallel. Cannot happen like that. Okay. Zinsu, Chong Zinsu, am I answering a question? Okay, great. Okay, if no more question, we shall end our lecture today. Take care, guys. Okay, see you all on when our next class. Today is Monday. Next class is Wednesday. All right. Okay.